Hello everyone, welcome to IKSR chemistry classes. Here we are in lecture number 2 on electronic spectra of complexes. In this video, we will discuss selection rules. Let us first of all see what is the need of selection rules. Are all the electronic transitions, that is transition of a molecule or ion between electronic energy levels, are equally probable or not. Let us illustrate taking with an example. This is a typical molecular orbital energy level diagram of an alkene, such as ethene, which has sigma bonding and sigma anti-bonding MOs. At the same time, it also has pi bonding and pi anti-bonding MOs. Here, two electronic transitions, that is transitions between electronic energy levels, have been represented by red arrow and green arrow. The electronic transition represented by red arrow, that is from sigma to pi star, does not take place, while the electronic transition represented by green arrow from sigma to sigma star takes place by absorbing UV light. Here we see that all the electronic transitions are not equally probable. Some electronic transitions are allowed, while some other electronic transitions are forbidden. That is, the electronic transition is formalized into forbidden and allowed categories. Now let us see what are the selection rules for electronic transitions. There are various selection rules for the electronic transitions, that is transitions between electronic energy levels. For electronic transitions between electronic energy levels of a molecule or ion, there are some selection rules which permit us to predict that which type of electronic transition will be allowed or forbidden. The first one is symmetry selection rule. The second is Laporte orbital selection rule, and the third one is a spin selection rule. We will discuss all these three selection rules for electronic transitions one by one. Let us first of all see symmetry selection rule. But before starting symmetry selection rule, let us see symmetry of orbitals. The orbital, which may be atomic orbital or molecular orbital, having center of symmetry, that is I, is called gerade orbital. The orbital having center of symmetry is called gerade orbital. It has even parity and it is denoted by G. G stands for gerade. On the other hand, the orbital, again, which may be atomic orbital or molecular orbital, having no center of symmetry, is called ungerade orbital. It has odd parity and it is denoted by U. U stands for ungerade, while G stands for gerade. Let us see it again. The orbital having center of symmetry is called gerade orbital and it is denoted by G, while the orbital having no center of symmetry is called ungerade orbital and it is denoted by U. symmetry of atomic orbitals. Let us see the symmetry of some atomic orbitals. First of all, let us define the center of symmetry of atomic orbital. If any line passing through a point within an orbital meets identical lobes or lobe parts on both the sides at equal distances, that point is called center of symmetry. If we pass any line through a point within an atomic orbital or molecular orbital meets identical lobes or lobe parts on both the sides at equal distances, that point is called center of symmetry, that is I. This is S atomic orbital. If we pass a line through the center of S orbital, we get equal lobe parts, identical lobe parts on both the sides at equal distances, and hence S orbital has center of symmetry present here. Therefore, S orbital is gerade orbital and it can be represented by G. On the other hand, if we pass a line through this point present in p orbital, we get different lobes on both the sides. This lobe is positively charged while this lobe is negatively charged, and hence p orbital has no center of symmetry. It is ungerade atomic orbital and it can be represented by U. S orbital is gerade while p orbital is ungerade. And let us now see what about d atomic orbital. If we pass this line, we get identical lobes on both the sides, and if we pass a line in this direction, we also get identical lobes on both the sides at equal distances, and therefore this point in d atomic orbital is center of symmetry. This is why d atomic orbital is gerade atomic orbital and it can be represented by G. S orbital is gerade, p orbital is ungerade, d orbital is gerade, and try to find out the symmetry of F atomic orbital, whether F atomic orbital is gerade or ungerade. Symmetry of molecular orbitals. This is sigma bonding MO. If we pass a line along this direction, we get equal lobe parts on both the sides at equal distances, and hence sigma bonding MO has center of symmetry present here. It is gerade molecular orbital. Now what about sigma star, that is anti-bonding sigma MO? If we pass a line through this point, we get different orbitals on both the sides, and therefore sigma anti-bonding MO does not contain center of symmetry. It is ungerade orbital. On the other hand, pi molecular orbital is ungerade because if we draw a line in this direction, we get different lobes on both the sides of this point. Therefore, pi bonding MO is ungerade. And what about pi anti-bonding MO? If we consider this point and pass a line through this point, we get equal lobes, identical lobes on both the sides at equal distances, and on passing the line in this direction also we get identical lobes on both the sides at equal distances of this point, and therefore this point is center of symmetry in pi star MO. Therefore, pi star MO is gerade molecular orbital, which can be represented by G. Let us recapitulate again. Sigma bonding MO is gerade and sigma anti-bonding is ungerade, while the situation is reversed in the case of pi bonding MO. Pi bonding MO is ungerade and pi anti-bonding MO is gerade. And now symmetry selection rule. What is symmetry selection rule? Only those electronic transitions, that is, only those transitions between electronic energy levels are allowed which lead to inversion of parity of orbital. Let us recapitulate again. Gerade orbital has even parity, while ungerade orbital has odd parity, and only those electronic transitions are allowed which lead to inversion of parity of orbital. In other words, the electronic transitions involving gerade and ungerade orbitals are symmetry allowed. Let us illustrate it. While the electronic transitions between two gerade orbitals or two ungerade orbitals are symmetry forbidden. If electronic transition takes place between gerade and ungerade orbitals, the parity of orbital is inversed and such electronic transitions are allowed. On the other hand, if electronic transitions takes place between two gerade orbitals or two ungerade orbitals, the parity remains the same and such electronic transitions are forbidden, while the electronic transitions taking place between gerade and ungerade orbitals are symmetry allowed. On this basis, the allowed and forbidden transitions are given below. If we consider transition from gerade to ungerade orbital, it will be symmetry allowed. Similarly, if transition takes place from ungerade orbital to gerade orbital, it will also be symmetry allowed, because these two electronic transitions lead to inversion of parity of orbital, that is symmetry of orbital. And if electronic transition takes place between two ungerade orbitals or two gerade orbitals, the symmetry will remain the same and such electronic transitions will be symmetry forbidden. Accordingly, the allowed and forbidden electronic transitions between various atomic orbitals are given below. If transition takes place from s orbital to p orbital, the parity is inverted, gerade orbital to ungerade orbital, it will be symmetry allowed. On the other hand, the transition of electronic transition from p orbital to d orbital also leads to change in parity of orbital. It involves ungerade orbital and gerade orbital, and hence it is also symmetry allowed transition. And if transition takes place from s orbital to d orbital, that is from g orbital to gerade orbital, it will be symmetry forbidden. And the transition from d orbital to d orbital, that is dd transition, the electronic transition which takes place between two d atomic orbitals is called dd transition, and it is symmetry forbidden because it does not lead to change in parity of the orbital. S to P is symmetry allowed, P to D is symmetry allowed, but S to D or D to D is symmetry forbidden. Similarly, the allowed and forbidden transitions between various molecular orbitals are given below. If transition takes place from sigma bonding MO to sigma anti-bonding MO, it will be symmetry allowed because the transition takes place between gerade and ungerade orbitals. The transition from pi bonding MO to pi star MO is also symmetry allowed because it involves ungerade and gerade orbitals. On the other hand, the transition from sigma bonding MO to pi star MO, as discussed in the previous slide, is symmetry forbidden because it involves gerade and gerade orbitals. This electronic transition sigma to pi star involves two gerade orbitals and it does not lead to change in parity of orbital and hence it is symmetry forbidden. Similarly, the pi to sigma star electronic transition involves ungerade and ungerade orbitals and this will also be symmetry forbidden transition. The second selection rule is Laporte orbital selection rule. Only those electronic transitions between various orbitals are allowed which involve change in azimuthal quantum number by unity. Only those electronic transitions between various atomic orbitals are Laporte allowed which involve the change in azimuthal quantum number, that is L by unity. It means the electronic transitions involving delta L equals to plus minus 1, that is change in azimuthal quantum number takes place by unity, are Laporte allowed. On the other hand, the electronic transitions involving delta L equals to 0 or plus minus 2 are Laporte forbidden. In nutshell, we can say that the electronic transitions which lead to change in azimuthal quantum number by unity are Laporte allowed while the other ones are Laporte forbidden. Let us illustrate it. The value of delta L is given by the expression delta L equals to azimuthal quantum number of in the final energy state, while Li is the azimuthal quantum number in the initial energy state. Lf azimuthal quantum number of the final energy state and Li is azimuthal quantum number of the initial energy state. Let us illustrate it with help of an example. Let us examine some electronic transitions and predict whether they are Laporte allowed or forbidden. If transition takes place from s orbital to p orbital, delta L equals to final L minus initial L. The value of L for p orbital is 1 and the value of L for s orbital is 0. Delta L equals to plus 1 and hence it will be Laporte allowed. If transition takes place from S to D, that is gerade orbital to gerade orbital, involves delta L equals to plus 2 and it will be Laporte forbidden. The value of L for D is 2 and the value of L for S is 0 and therefore delta L equals to plus 2. Only those electronic transitions will be Laporte allowed which involve delta L equals to plus minus 1. Let us now consider the transition from d orbital to d orbital. It will have delta L equals to 0 and therefore it will be Laporte forbidden. And finally, let us see transition of electron from p orbital to s orbital. The value of L for s orbital is 0 and for p orbital is 1. The value of delta L will be minus 1 and hence it will be Laporte allowed. And now finally we see a spin selection rule. Only those electronic transitions between the electronic energy levels of a molecule or ion are allowed which don't involve any change in a spin multiplicity. That is, no change in 2s plus 1 or s. Only those electronic transitions between electronic energy levels of a molecule or ion will be symmetric, will be a spin allowed, which involve no change in a spin multiplicity, that is 2s plus 1, and 2s plus 1 will not change when the value of s does not change, and s is nothing but resultant a spin angular momentum quantum number. It means the transition involving delta s equals to 0 is a spin allowed if during any electron transition a spin multiplicity does not change, delta s will be equals to 0, and such electron transition will be a spin allowed. And the electronic transition which involves delta s not equals to 0 will be a spin forbidden. Only those electronic transitions will be a spin allowed which involve delta s equals to 0, that is no change in s or a spin multiplicity. The value of delta s, that is change in resultant a spin angular momentum quantum number, is given by delta s equals to sf minus si. Here sf is resultant a spin angular momentum quantum number of the final energy state, and si is the resultant spin angular momentum quantum number of the initial state. Let us illustrate taking an example of electronic transition in MnH2O whole 6 2+. It has manganese in +2 oxidation state with 3d5 electronic configuration, and H2O is a weak ligand, and therefore MnH2O whole 6 2+ will be a high spin complex having 5 unpaired electrons in the initial state. These are 5 unpaired electrons, and initial value of S, that is Si, will be 5 by 2, number of unpaired electrons by 2. If the transition of this electron takes place from T2g orbital to Eg orbital by absorbing electromagnetic radiation from visible UV region, this electron will get paired up here according to Pauli's exclusion principle, and in the final state, that is excited state. This is DD transition in MnH2O whole 6 2+. The number of unpaired electrons will be 1, 2, 3, and therefore resultant a spin angular momentum quantum number in the final energy state will be 3 by 2. The spins of these two paired electrons cancel each other. Let us calculate now delta S, S final minus S initial. Final S is equals to 3 by 2 and initial S is equals to 5 by 2. The value of delta S is -1. Any electronic transition will be a spin allowed only when delta S equals to 0, but here delta S equals to -1, and therefore the electronic transition in MnH2O whole 6 2+ is a spin forbidden. Let us consider another example of FeH2O whole 6 2+. It has iron in +2 oxidation state with 3d6 electronic configuration. This complex is also a high spin complex because H2O is a weak ligand. The first electron, second, third, fourth, fifth, and sixth. There are 4 unpaired electrons in the initial energy state, and therefore Si will be equals to 2. If this electron having downward spin is promoted to higher energy level by absorbing UV visible light, this electron gets paired up in the EG state of orbitals, and the number of unpaired electrons in the final energy state, excited energy state, is also equal to 4, and therefore SF will be equals to 4 by 2, that is 2. And let us now calculate the value of delta S, which is equal to SF minus SI. SF is 2 and SI is also 2. Therefore, delta S will be equal to 0. That is, the electronic transition in FeH2O whole 6 2 plus does not lead to change in a spin multiplicity, and hence it will be a spin allowed transition. Thank you for watching the video with patience and concentration.